All right, so we're going to finish up 2 of the notes with this video. And in this video, we're talking about measures of position. Now, measures of position is exactly what it sounds like. It's where we are located within the set, or where one individual is located within the population compared to everybody else. So if I were talking about my measure of position, I could talk about maybe how tall am I compared to everyone else in the class. Now, the first measure of position we're going to look at is what's called z-scores or z-values, okay? And we actually saw this when we were dealing with Chebyshev's rule and the empirical rule, because we calculated the number of standard deviations away from a mean that a data point was. Now, if we're dealing with a population, then the z-score or z-value is just going to be the value that we're looking at, subtract the average, and divide by the standard deviation. Notice that's the population average, and that's the population standard deviation. If we're dealing with a sample, it's the exact same thing, except we're using a sample average and a sample standard deviation. So we take whatever value I'm trying to find the z-score of, subtract the average, divide by the standard deviation. All right, and that's always gives us number of standard deviations away from the mean. So just to remind you of that, if you remember when we dealt with the third example of Chebyshev's theorem, we had an average of 80, and we were looking to find out how far away 54 was in terms of standard deviations. In other words, how many standard deviations is 80 from 54? So what we did is we took 54 and we subtracted 80, and we said, well, the difference between 54 and 80 is 26 units. It's a negative 26 because 54 is to the left of 80. And then since each standard deviation comprised of 5 units, we divided by 5. So negative 26 divided by 5 became negative 5.2. So now with the notation we have, we can figure out that what really this was the z-score of 54. All right, so the z-score of 54 is negative 5.2. And then similarly, when we had an average of 80 and a standard deviation of 5, we looked and we said, okay, 92 is how many standard deviations away from 80. So to find the z-score or the z-value of 92, what we would have had to have done is say, well, 92 is 12 units away from 80. Each standard deviation is a jump of size 5, and that came out to 2.4. So we would say the z-score of 92 is 2.4. Now we're going to do this for the texts the text that we had earlier. So earlier we had this example of the number of ancient manuscripts. In fact, if you haven't changed your calculator, this is probably still in list 1. So we're going to find the z-scores of this example. Now specifically, we're going to find the z-score for the Herodotus, z-score for the New Testament, Aristotle, and Tacitus. Now, in order to find z-scores, what we have to do is we have to be able to find the mean and standard deviation. We saw how to do that in previous videos, but just as a quick refresher, we're going to go into Stats, Edit. We're going to make sure L1 has all of these data. So 8, 8, 5, 10, 20, 9, 7, 7, 0, and 5,600. Then we're going to go into the calculate. We're going to calculate one variable statistics in L1, and you should get the same display as we always have. So the average you should get is 567.4 with a sample standard deviation of 1768.28. So let's just take a moment to figure out or to realize what that means. First off, Herodotus has an ancient text number which is 8. The New Testament has an ancient text number which is 5,600. Aristotle has an ancient text number which is 5. And Tacitus has an ancient text number which is 20. So here's what we're doing. What we're doing is we're saying, well, first off, let me type in. So we found that our X bar was equal to 567.4. By the way, I'm saying that this was a sample of ancient texts because that's what we used when we calculated the standard deviation. When we calculated the standard deviation previously, we used that it was a sample of ancient texts. So we're going to use the sample standard deviation of 1768.28. So the ancient manuscript data has those as my mean and standard deviation. Herodotus, like we said, had a value of 8. So the z-score for Herodotus, or the z-value for Herodotus, would have been equal to, well, since the value was 8, the difference between 8 and 567.4 divided by 1768.28. So we're going to type that into our calculator. I'm going to give a decimal version of that. So once I type this into my calculator, 567.4, excuse me, 8 minus 567.4, divide that by 1768.28, and we get a negative 0.32. Whoops. So equals negative 0.32. So the z-score for Herodotus is negative 0.32. Now I'd like you to just practice calculating z-scores. Calculate the z-score for the New Testament, the z-score for Aristotle, and the z-score for Tacitus. I will push pause on the video and let you do all of those. All right, so hopefully you push pause, calculated those. I'm going to do those pretty quickly and on the next page. So here we go. Let's take a look at the New Testament. We saw the value, the number of ancient manuscripts in that the New Testament has is 5,600. We take that, subtract the average of 567.4, divide by a standard deviation of 1768.28, and we find that the New Testament has a z-score, or a z-value, of 2.85. So the New Testament is 2.85 standard deviations above the average. And we saw earlier that Herodotus was 0.32 of a standard deviation below the average. Similarly, Aristotle, the value there is 5. the z-score comes out to be negative 0.32. Now, I'm rounding this to two decimal places. If you rounded this to 3, it would be a slightly different between Herodotus to Aristotle, but rounded to 2 decimal places, these two have the exact same z-score or z-value. So that means that rounded to 2 decimal places, they're basically both negative 0.32 standard deviations away from the mean. So in other words, 0.32 standard deviations to the left of the average. Tacitus similarly has a value of 20. So when you look at Tacitus, Tacitus has 20 ancient manuscripts, and that translates into a z-score of negative 0.31. The difference between 20 and 567.4 is divided by 1768.28 becomes a negative 0.31. So if I look at these three, z-score wise, z-value, Herodotus and Aristotle and Tacitus all look very, very close to the same, very close to the same location. They all look about negative zero point 0.3 to the left of the mean. Whereas the New Testament, it's way out there. It's 2.85 standard deviations to the right of the mean. So that's the sort of impression we get with z scores and z values. Now, one thing I do want to mention, those examples, I use this second formula because we were using samples. But again, if you were given a population average and a population standard deviation, we do use this formula up here. But they're calculated the same way. It's your value minus your average and then divide by your standard deviation. So that's z-scores. The next type of position that we want to look at is ranking. Now, this is a really simple way of talking about, excuse me, this is probably the simplest way of talking about positions. It's saying like, well, I am the 5th tallest in the class, or I am the 7th shortest in the class. One thing I do want to say about rankings, when we're given quantitative variables, we're always going to go lowest number gets rank 1, and then from there we go greater and greater and greater up till we get to the greatest number. So in other words, we're going to rank always from smallest to largest. And the reason we do that is so that we match what our calculator is doing. Our calculator is going to rank things from minimum to maximum. So what we're going to do is we're going to start, let's do a ranking of these texts here. So again, same example we've had, let's rank them. Now again, we have to go numerically from least to greatest. So Homer's Iliad will be rank 1 because that is the lowest score. Let me go into a different view of this so that we can actually rank things. So we have this in a Word document. I'm going to go over here and rank things. So this would be rank 1. And then the next smallest number is Aristotle. So Aristotle would be rank 2. Actually, I should just put a little R there. Now, kind of something weird happens at the next highest. We tie at Pliny and Plato, both have 7 ancient copies. And so what we have to do in this case, since there's really no tiebreaker, what we have to do is we have to rank both of these the same. By the way, when I say there's no tiebreaker, what I'm saying is that if I were talking about people's ages, all right, and I would say, well, I am the same age as my old college roommate. Well, because we're the same age, we might have displayed the same exact age number, but one of us might be a month older than the other. So that's what I mean by tiebreakers. Sometimes when people display numbers, they're actually sort of a tie, there may be a tiebreaker. In this case, there's no such evidence for that. And so we have to rank both Pliny the Younger and Plato as rank 3. Now, in order to not throw off our count, what we have to do then is say, well, I've ranked a total, even though I went up to rank number 3, there's actually 4 manuscripts that I've already done. So the next one we come across, what I have to do is I have to rank that not as 4, but rather as 5. So I skip over a 4 because I have 2 3s. And by the way, there's a tie at 8 as well. So we'll give both 8s rank 5. And then the next highest number is 9. And so what we have to do is we have to rank that one as not 6, but rather 7. So I skip over a 6 because I have 2 rank 5s. And the seventh number from the bottom is 9, which is basically the ranking of Josephus. 10 is going to have rank 8. 20 is going to have rank 9. And then the New Testament at 5,600 has the top rank 10. So we can see how these things are ranked. And so when we go down and say, well, what is the ranking of Herodotus, for example, we would go look at this and say, oh, Herodotus was rank 5. The New Testament. Well, the New Testament, we go up here, rank 10. Aristotle had a rank of 2, and Tacitus had a rank of 9. Now, I want you to take just a moment to look at the rankings versus the z-scores. The impression we get after we look at z-scores is that Herodotus, Aristotle, and Tacitus are all really close, and the New Testament is far away to the right. The impression that you get with rankings is very different. In terms of rankings, it looks like the New Testament and Tacitus are really close. One of them's ranked 9 and one of them's ranked 10. And it looks like, Herodotus and Aristotle and Tacitus are all fairly well spread out. Based on rankings, you probably think that Tacitus is closer to the New Testament than Herodotus is to Tacitus. But that's obviously not true in terms of the actual values and in terms of the actual z-scores. So that's what you should notice about the differences between rankings of z-scores and between z-scores and rankings for this example, that they give very different impressions. By the way, this is just another example of changing the subject. So if I wanted to make it seem like Tacitus and the New Testament were far apart, I'm going to use z-scores or I'm going to use the raw numbers. Whereas if I want to make them look really close, maybe I use rankings. So that's something to watch out for um, in terms of rankings, okay? So what we have to do when we look at rankings, we have to realize, well, there's a lot of different ways to mislead, but I want to mention two of them right now. Okay, the first way to mislead is by having big gaps in the data where, for instance, in our example, there was a big gap between Tacitus and the New Testament, but rankings didn't really tell us anything about that gap. You know, an added one ranking between Tacitus and the New Testament, that was a jump of like over 5,000 ancient manuscripts. Whereas a jump of one ranking between some of those were only a jump of like precisely one ancient manuscript. The jump from 7 to 8 ancient manuscripts, or 8 to 9 ancient manuscripts, or 9 to 10. So always be wary of that. So if somebody gives you a list of rankings, one thing you should ask is, well, what is the difference between the rank number 1 and the rank number 5? What's the actual measurement distance that we can look at? The other thing that we should be aware of when we talk about rankings is that oftentimes rankings can be subjective. What subjective means? It's basically somebody's opinion. So if I give you a list of the 10 greatest songs that were ever written, you might step back and say, well, wait a second, what makes those the greatest? And if I gave you a list of the 10 greatest songs ever written, it's almost guaranteed to be some sort of a subjective ranking. Because obviously people's opinions differ. My opinion may differ from yours, yours may differ from your grandparents, all of those types of things. And even when y- and you see this a lot, even when it's sort of self-professed experts and they gathered lots of experts and they're sort of averaging out the experts, it's still some sort of a expert's opinion. So it's still opinion based. It's still a subjective ranking system. Now, objective ranking systems are a little bit different. Objective rankings are simply saying that it's some sort of a measurement. So we could judge best songs based on number of YouTube clicks. Now, would that be the real greatest way to figure out what the best songs ever written are, based on YouTube clicks? Probably not, but it would be objective. Okay, so anything that I can measure numerically, that doesn't deal with somebody's opinions, then that's objective. Okay, but even in objective rankings, we have to realize that there are some when I say, again, let's go take the example of best songs. When I say, well, let's make an objective measurement of what the best songs ever written were. Well, you may do that based on the number of YouTube clicks, and I may do that based on the number of records sold. And we may get very different lists because records sold is not the same thing as YouTube clicks. And we could all probably figure out that, during certain time frames in history, YouTube is very popular now, but it wasn't 20 years ago. And that may sort of bias the types of songs that get a lot of clicks in YouTube. If I did record sales, maybe the, record sales would be higher 20 years ago than it is now before, the advent of, buying songs on the internet and things like that. So uh, we have to, again, watch out for the subjective versus objective rankings. And then even within the objective, we have to watch out for, well, how did you measure it? What was the metric that you used to be able to say this is the best song? You'll see this often too in basically any type of system. They'll, people will say, well, what's the best healthcare system? And obviously, we could make that subjective, but we could make it objective too. But the concept of healthcare is such a broad concept that there's many different ways to make it objective. And the United States may rank really poorly if we want to have um, an objective ranking based on price. But it would probably rank, it does rank really high if we're talking about results. So if we're talking about like, people get, when I say results, I mean like people recovering from getting a cancer or people being satisfied with their stay at the hospital, those types of things. So objective rankings, um, always look into how did people make the list? Was it subjective? Was it objective? And then if it was objective, what type of objective measurement did they put on it? All right, so the next type of um, measure of position we're going to look at deals with percentages, okay? And when basically we understand that rankings are really nice, you just talk about, 1, 2, 3, 4, 5. But the nice thing or the downfall of rankings is that when you get into really, really big populations, and I do a ranking, it's oftentimes hard to get our heads around something like, well, we rank 1,287,000 out of 4,623,178. That's really hard to get our heads around. And so what we like to do is we like to make it a percentage. Now, we all kind of know what percentages are. In this class, when I'm talking about measures of positions, percentages can always be calculated by just taking the rank divided by the total and then multiplying by 100%. Okay. By the way, the book does a little uh, slight adjustment to that. They'll do rank minus zero point 0.5 divided by total and then times 100%. We're not going to worry about that because, like I said, percentages are most handy when the total is really hard. So doing any sort of adjustment to the rank is not going to be a big deal. So in this class, we can just make it simple. We'll do rank divided by total and then multiply times 100%. Now again, why do we want to do this? We want to do this when we have really large populations. And if there are those of you who have children, you've probably seen growth charts like this. It wouldn't make sense for you to say, well, out of all 12-year-old boys, and I'm looking at the weight of 12-year-old boys, um, 90 pounds ends up there. And so what would the trace that out and what percentage that would be? About the 50th percentile. So we've seen these things, percentages before. I'm not going to have you read growth charts or anything like that, but what I would have you do is make a percentage based on, or a percentile based on something like this data. So let's go to Herodotus in the New Testament and Aristotle and Tacitus again within this data. And percentages, again, they don't have to deal with these raw numbers. All we're dealing with is the rankings. So Herodotus had a ranking of 5. So if I take 5 divided by 10, we get 0.5. Move the decimal over 2 spaces by multiplying times 100%. 5 is 50th percentile. New Testament is a 10 out of 10. So 10 divided by 10 times 100 becomes 100%. So the New Testament is the 100th percentile based on the way I'm calculating it. Now, by the way, again, the book does it slightly different. They adjust it down a little bit so that this 100th is actually the 95th percentile. Aristotle, let me scroll up. I forgot what Aristotle's ranking was. Aristotle's ranking was 2, and so that would have translated into 20th percentile. Tacitus, well, Tacitus had a ranking of 9, so that would translate into the 90th percentile. Now, just as a side note, be careful. In this case, the reason why we were always dividing by 10 is because we had 10 ancient manuscripts. If, for instance, I went back to one of the examples I had before. So this is an example that came out of earlier in chapter 2. We had 10, 12, 13, 18, 20, 24. If I wanted to find the percentile of, let's say, 13, I've ordered these so that it goes from least to greatest already. So what I would have done is said 13 is in the 3rd spot, so that gets ranked 3 out of 1, 2, 3, 4, 5, 6 other numbers. So the 3 out of 6 times 100 would have been, would have been the 50 percentile, okay? And similarly, if I would have done the percentile of 20, well, 20, excuse me, is in the 5th spot, so it's rank 5 out of a total of 6, and I would have multiplied times 100 to get, well, this one doesn't come out quite as nice and even, but we can still round that to 2 decimal places. So 20 would have gotten a percentile of 83.33%. So that's how percentiles are going to be done in this class. Again, the book does that slightly different, but that's how we're going to keep it kind of nice and easy. Now, there are some key percentiles that we always want to consider looking at when we deal with a set. And those key percentiles, well, we already saw one of them. The median is really the 50th percentile. It's where the one where 50% is above, 50% is below. By the way, just to make the point, that's why the book always wants to add 0.5, because they would have had the 50th percentile, meaning right between 13 and 18, instead of being on 13 itself. So that's why the book does that, but we don't need to do that. So we already saw the median, that's the 50th percentile. And in some sense, the minimum is sort of like the 0th percentile. And in some sense, the maximum is sort of like the 100th percentile. But there are 2 other percentiles called the quartiles that are also important. And they're just the 25% and the 75% mark. Now, the notation for the first quartile is called Q1, and it's the 25% mark. The third quartile is called Q3, and it's the 75th percentile mark. And the nice thing about quartiles is that if we want to find them on this data set, it turns out they were already there on our calculator. We probably just didn't look at them enough. So if you remember back, just a few slides ago, or just in earlier this chapter, we should have these data in list 1 of our calculator. And we've been a lot of times going back into one variable stats, L1 for our list, and hitting enter. Well, that's what we're going to do now as well. All right. So we just go back to one variable one variable stats, hit enter. And what you'll find is you'll find at the very bottom of the one variable stat stuff, you'll find what people call the 5-number display. And the way it's set up in ours, it'll say the minimum x is 0. It'll say Q1 is 7. It'll say the median is 8. Should say Q3 is 10. And then the maximum x value is 5,600. So this is, again, it's called the 5-number display often. I'm going to make that, try to match the calculator display as much as possible. So the minimum x value, Q1, the median, Q3, and the maximum x value. Okay, so again, that's in the same exact, we've only used basically one function, stat edit, and then one variable stats. So one variable stats, list 1, gives us at the very bottom this 5-number display, which tells us the minimum, the first quartile, the median, the third quartile, and the maximum. So that's how we find the quartiles, or at least that's how we find the quartiles in the easiest way possible. Now, the reason we kind of not like to find the quartiles is because the quartiles give rise to the interquartile range. And what the interquartile range does, it gives us a measurement for how spread out the middle part of our set is. So in other words, the interquartile range, if you think about it, it goes from the 75th percent mark to the 25th percent mark. The gap between 75th percent and 25th percent is 50%. And so the interquartile range gives us the range of the middle 50% of the data, the middle half of the data. And all we do to find the interquartile range is look at the difference between the third and the first quartile. So it's calculated as take Q3 and then subtract Q1. So if we wanted to find the interquartile range of our set, whoops, I forgot to write that down, didn't I? Over here. So we said the minimum was 0, the first quartile was 7, the median was 8, the third quartile was 10, and the maximum was 5,600. So in our example, the interquartile range is the range between 10 and 7. So it'd be 10 minus 7, which is 3. So that's it. Our interquartile range is 3, right? The difference between 10 and 7. So notice how that differs from the actual range by a lot. The actual range would have been 5,600 minus 0. In fact, we calculated that, I think, earlier. So what it's saying is that the distance between the bottom and the top number is enormous, but that middle 50% is pretty tight. It's really only a 3-unit gap from 7 to 10. So the middle 50% of the data is really fairly narrowly, it's fairly compact. Okay. And while interquartile ranges are nice to deal with, their real importance comes when we're trying to calculate outliers. An outlier is simply an extreme value, meaning when I'm talking about quantitative data, a value that's unusually high or unusually low. Now, the term unusually high or unusually low is arbitrary, right? I can say somebody is really tall, and compared to me, maybe somebody is who's 6 foot is tall. But compared to somebody else, somebody who's 6 foot might be short. So what we like to do in statistics is officially define things numerically so that we don't get stuck in sort of arbitrary subjective lands. So instead of saying unusually tall or unusually short or unusually large or unusually small, what we do is we say an outlier is anything below Q1 minus 1.5 times the interquartile range. Or an outlier, so that's our unusually low number, is anything below Q1 minus 1.5 times the interquartile range. Our unusually high number is anything above Q3 plus 1.5 interquartile range. So basically what I'm doing is I'm taking the middle 50% of the data and I'm saying go 1.5 interquartile ranges above that and 1.5 interquartile ranges below that. And that gives us our bounds for outliers. So let's take our outliers example, or excuse me, our manuscript example, and ask ourselves, are there any outliers? Now, we're going to do this officially, but I bet that if I just showed you this data set, when we first saw it, almost everybody would have agreed that the New Testament must be an outlier. It just looks much, much bigger than everything else in the data set. And it turns out that the New Testament, in this case, in the number of ancient manuscripts, is an outlier. But let's calculate it officially. And let's see if there are any others other than the New Testament that might be outliers within this set. So we found that Q3 is 10, Q1 is 7. So our interquartile range was 3. Whoops. So an outlier is anything below Q1 minus 1.5 interquartile ranges. And what that would have meant is it would have meant that it's below, our Q1 was 7, so 7 minus 1.5 times our interquartile range of 3. So if you type that into the calculator, 7 minus 1.5 times 3, we get out that anything below 2.5 would have been an outlier. Now let's go to the other extreme. Anything above Q3 plus 1.5 times the interquartile range. So anything above, well, Q3 in our example was 10. We'd add on 1.5 times 3. So anything above a 14.5 would have been an outlier in our example. So let's look for some outliers. If we look for some outliers in this text, do we have anything below 2.5? Sure, Homer's Iliad is below 2.5. So Homer's Iliad would have been an outlier because it's too low. Now, no other number goes below 2.5, so Homer's Iliad is the only one that goes below that lower bound of 2.5. Now, which ones go above 14.5? So the upper bound on the outlier is 14.5. Notice that obviously the New Testament beats that by enormous amounts. So it's a gigantic outlier. But also, if you look up here to Tacitus, Tacitus is at 20. So because 20 is above 14.5, Tacitus is also an outlier. So this data set has three outliers. It has Tacitus, the New Testament, and Homer. And all three of those numbers, all three of those ancient texts are outliers in this data set. So any outliers? Yes, the New Testament is an outlier, but also Tacitus and also Homer. All right? So we have three outliers in this data set. And by the way, that's one of the reasons I keep using this, kept using this data set, is it's because it gives me some nice illustrative ways to talk about things like the differences between rankings and z-scores, but it also is unique in the sense that it has three outliers amongst a set of size 10. That's fairly unusual. Uh, it doesn't happen a whole lot in real life, and this is a great data set for that. Now, there's another reason I wanted to use this as well, and that is because it talks about things like the New Testament. And I talked to you at the end of chapter 1 about being able to use religious or politics or stuff like that. Obviously, the New Testament is a religious book, and so I wanted to include that so that I could demonstrate that, none of these calculations are controversial because I used a religious book. That's just the way it is. And in fact, why did we get so many numbers um, why did we get so many copies of the same New Testament? Well, that's because that's what monks did. They took those original letters and they just copied them down, and that's what they did. They copied them down, recopied so on and so forth. And they're pretty thorough. So oftentimes you'll see religious books having lots of copies of the same thing because people spent lots of time and effort, recopying those same manuscripts. Whereas something like Tacitus is a history book. Um, while that was, copied by Rome, it's not, it doesn't have the same weight to it. They didn't need to distribute it out to all kinds of places like the New Testament had to be distributed out. So again, none of these data are controversial, and I'm trying to practice what I preach and mimic what I talked about in chapter 1. So that is the end of section 2.2. Let me state one quick other thing about 2.2, and I'll use the PowerPoints to do that. Some of you have seen a lot of formulas. Like I said, as far as formulas go, the formulas for standard deviation, the formula for mean, you should be able to match that. So you don't have to have that memorized. Range, mid-range, you should have those types of things memorized. Those are just, halfway between. If we know what it's doing, we know the calculations. This formula that we saw in Chebyshev's theorem, what I would do on the test, if I ask you a question about Chebyshev's, I would have a hint that says hint 1 minus 1 over k squared. I believe that happens in my homework as well. So if you check on your homework, it'll kind of look like that. It'll say hint 1 minus 1 over k squared. So Chebyshev's theorem will look, there'll be a question. It'll say something like, the average score on a test is 80 points with standard deviation of 5. What percentage of people must have scores between 70 and 90? And then it'll say, hint 1 minus 1 over k squared. And similarly, with the empirical rule, what I would have on the test, it would say hint 68%, comma, 95%, comma, 99.7%. So you won't have to memorize those numbers for the test. You'll just have to realize, oh yeah, that first number, 68%, that was within 1 standard deviation. And you'll have to figure out what 1 standard deviation is. Same thing, 95%, oh yeah, that was within 2. 99.7 was within 3. So I'd give you a hint, and I'd give you all 3 of those percentages. Excuse me. As far as measures of positions, this is one that you should know. All right, so this is a formula. I will ask you questions about z-scores, and you will need to know how to calculate z-scores without a formula. All right, so that is something you're going to have to know. And the reason I have you do that right now is because we're going to do that at a few places during the semester, talk about z-scores. So I really want us to know what z-scores are. You should be able to do rankings on your own. There's no formula for that. You should be able to do percentages on your own. That you shouldn't need a formula for calculating a percentage or a percentile of an object. As far as the interquartile range, well, the name gives it away, interquartile range. So you should know how to do that on your own. Calculate Q3 minus Q1. As far as the outliers go, these are also formulas where I would give you a hint on. So if I ask you to calculate, is the New Testament an outlier, or is Tacitus an outlier, I would say hint Q1 minus 1.5 times IQR, Q3 plus 1.5 times IQR. So I'd give you that hint within the problem, just like I was talking about earlier. So as far as formulas go, again, make sure you know how to calculate all the measures of positions. The z-score is the one I see people mess up most often. So make sure you know how to do z-scores. Make sure you know how to do percentiles, and realize that, hey, z-scores are dealing with the actual values, percentiles are dealing with the actual rankings. So know how to calculate those, but as far as something like Chebyshev's rule, as far as something like empirical rule, as far as something like these outlier calculations, I would give you hints for all of those. All right, so that is the end of section 2.2. Next video is on 2.3, and then after that, you'll be taking the test. So make sure you're practicing for the tests and things like that right now as you transition into 2.3.